and I am a course advisor for ECT. Welcome to today's webinar that will be presented by our Industrial Automation Program Leader, Dr. Shalan. So in order for us to have as little interruptions as possible, please could you take note of the slide in front of you right now? So if you could just switch off your notifications and sounds. And also, I'd just like to inform you that we do have a Q&A function, and that's just for you to be able to pose your questions, and we'll take the questions closer to the end of the presentation. And for today's webinar, we will have a certificate of attendance, and that will be sent to you within that will be sent to you within 4 business days of today's webinar. And there'll also be the copy of the slides and the video recording, which will be sent to you within 2 business days from today's webinar. Now, for each of the things I've mentioned, the certificate of attendance, the copy of slides and video recording, there's a survey at the end of this webinar that you'll need to fill out, which will expire in 48 hours from you receiving it. So once you fill that in, that will ensure that we get the copy of the slides, video recording, as well as the certificate of attendance to you, to the provided email. And if it's not in your inbox, it will be in your junk or spam mail. Now, just to let you know a little bit about ECT and what really sets us apart. So ECT is an engineering specialist college that offers industry-driven programs that offer UK recognized education. All of this is made possible by our lecturers and instructors, which are industry professionals. They've been in the industry for a while and they are very knowledgeable in each of the fields. So ECT, offers a unique delivery model. So you'll find that everything is agile, so to speak, in terms of your studies when you are studying with ECT. And for the event conduct, if you could just follow my instructions so we can have a seamless presentation, that will ensure that we actually get to it on time. And today's topic is the impact of industrial automation. It's a case study, and as I've mentioned, it will be presented by Dr. Shalan, and he is our industrial automation program leader. So, Dr. Shalan, if you don't mind, you can take control and you can begin with the presentation. Thank you.
Thank you, Komo. Hello, everyone. Welcome to this webinar, to this technical webinar. Thank you for taking the time to attend, and hopefully you are going to get some valuable knowledge as an output of this webinar. Please let me know towards the end of it if you had any questions, and we can have a good discussion about it. So today in general, it is all about understanding what is industrial automation, and as a case study, what can industrial automation do to impact the manufacturing industry. So as a start of today, I'm just going to give you a little bit of background on myself. So my name is Abdu Shalan, and I am the program leader for undergraduate and postgraduate industrial automation programs at the ACT. My background is mechatronics engineering, followed by engineering management masters, and then a PhD in industrial automation and advanced maintenance practices. I did carry out lots of different research and consultancy projects, jobs, however you want to say it or call it, over the years, which equipped me with lots of knowledge and lots of abilities to link industry with academia. And this is what we do at the ACT. We are different from any other university or institute in the fact that we focus on actual applications, actual industry, making you ready once you finish our courses that you already know what is an industry and you are ready to go. Today's agenda is going to have a few different topics. So we are going to talk about the industrial revolutions, how production lines operated, what is a PLC, inputs, outputs, what is a hydraulic system or a hydraulic press as our case study, and then the developed system that has been applied for this hydraulic press, and what is the impact of developed system on pure requirements. So everything must have a starting point, and when we are talking about industrial automation, we need to know what are the industrial revolutions. So when we talk about the industrial revolutions, we talk about the time when the transition time from when humans were making things using their own power source or using their own hands as a controlling or driving power source and using their skills to drive these tools. Like how we can see in this picture here, we can see that person is making some metal products, whether it is a sword, typically a sword, as it was back in the ages or the old ages. And that person is using his own power as the driving force for the tools, for that hammer, and using his own skills and her own skills in order to drive the tools to shape or to create the products that they want to produce. This has always been the case for centuries until the first industrial revolution came around, and that was around the 1780s. So when we talk about the first industrial revolution, we talk about one thing, and that thing is how can we use external power sources instead of our own power sources. And that was the highlight of the first revolution. It was the use of steam engines. When steam engines came out, they got involved with almost everything within our daily life activities. So they were the driving force for factories. They were the driving force for the transportation elements, like how we can see here. We can see a steam train. It was the same thing for the sea transport. So all the ships now started to have steam engines instead of the sails. We started to see it going around and happening in almost everything that we are dealing with. And that was the start as well when we started to have the first cars. It was the first car to replace a horse by a machine or a steam engine. So that was the highlight of the first industrial revolution. But with this, we started to have the need for extra developments. And this is when we started to see that, well, our factories now are more capable to make more products. And that was the highlight of the second industrial revolution. We started to have production lines. And the whole idea of production lines, it was, well, how can we streamline our products so we are not having that customization element anymore? In the past, before any production lines come to life, what we used to have customization element in everything that you do. So you go to the carpenter, you go to the blacksmith, you go to whoever making products, and you ask for different criteria, different shape, different dimensions of the product that you are looking for. But with production lines, we started to look into, well, we can make a lot with that external power source, but we have to streamline our products. Streamlining it means that we are eliminating the customization element. And this is what we can see here. And that was the first production line that has been developed, and that was by Ford in the US. And what you can see here, this is the Ford Model T car that was developed out of the first production line that has been made. What you can see here, you can see the exact same car across the whole line. The same color, the same shape, the same wheels, the same everything. This is a drawback, but in return, we had much larger capacity. So they can make much more of this car now. And this can be applied, and it is still happening until now, on the manufacturing industry. Any production line focused mainly on making one or two products variants, like how we can see with mobile phones, like how we can see with any products in general that you have. It is a one thing, and it is one model, maybe little variants, maybe little changes, but it is still the exact same platform that has been adapted to make the entire product. So that was the second industrial revolution. And with this, we started to have production line, as I said, and we started to have development in the railway and in the shipping industry. So we can now reach different places much easier, and we can distribute all that amount of products that we are making out of the production lines to different countries and different continents. With this, we started to have difficulties because with the steam engines, we started to have as well the emerging of electricity and its applications. And in order to control such a production line, that was the time before having any computers or anything. That was the way to control a production line. Then that was called the relay room or a relay control panel. So it's a big room that is full of relays and different circuitries that can manage the transition and the sequencing between the different parts of the production line. For example, that car, that Model T, it will start, or it will have, or the car itself, the chassis will stop at the body station for a certain amount of time, and then it will move towards the painting shop, and then it is going to move towards the assembly of the engine, the gearbox, the different interior, exterior, etc. So we needed sequencing operation. We needed to control that sequence of operations within our production lines, and that was the way to do so. What you can see here, you can see a hectic room, because if anything went wrong, or if you wanted to do any adjustments to this room, that's going to take a lot of time. And for this, it is going to have a lot of downtime. And downtime is when you are not producing. It's when the production line is stopping, and this is when you are losing money. So that was a big issue and a big drawback of such production lines. And that was the whole concept of the introduction of automation or computers. So what we started to have the first introduction of computers, and that was around the 60s, or the early 2000s, or towards the early 2000s, like how you have until now. So computers came around, so we started to have intelligence. We started to have the ability that we can write a piece of program, and that piece of program is going to be added to that controller, that computer, and that is going to replace that relay room with that intelligence element that it can create that sequence of operation in a much easier way. And this is what you can see now in modern factories for automotive, as an example. So you can see a lot of robotic arms, for example, and these are the driving force for any body shop within the automotive factory or the automotive industry. When you think about the automotive industry, it is not relying heavily on automation or whatsoever. It is mainly automated in the fact that, or fully automated, in the areas of the body shop where the chassis of the car is getting assembled and the painting chambers booth section of the factory. Everything else is semi-automated. So the assembly process of everything else happens with the aid of people. So it's not the machine is solely making the assembly, rather than there is a person that is using the aid of a machine to make the assembly process much easier and much quicker. So this is what you started to see in the modern factory, full production lines or big sections of the production lines that are fully automated, doing the job by themselves and relying on computers. The industrial version of a computer is called a PLC. A PLC is a controller that is designated or made specifically for industry, to work in a factory. To work in a factory means that it needs to be rugged or rigid, so it has to withstand all the different difficulties, issues that might exist that is surrounding the factory. So if you have any contaminations, any dirt, any water, any of these different things that can easily impact normal computer, PLC can withstand these issues. So what we are looking at here is we are looking at one of the hundreds of PLCs that exists in the market from a brand called Allen Bradley. Allen Bradley is a very established brand in making PLCs, or programmable logic controllers. This is what it stands for. So inside that box, what you find a controller, which is typically in that area in here. And that controller has the connectivity to two sides of ports in general. One port is called the inputs port, and one port is called the outputs port. We are going to talk about this. And in addition to this, you can find Ethernet or connectivity port. And this is, let's call it a recent development in PLCs, that it has the ability to connect to networks and to networks, or the Ethernet, so it can be communicated with from large distances. So what are these two sides of the PLCs? The PLC works as a human. So you as a human, you have your brain, and that brain is the processing unit. In order to make a use of that brain, you have all your inputs and all your outputs. All your inputs are the different sensors that gives you awareness of your surrounding environment. You have your eyes, you have your ears, nose, all the different senses. And based on this, you can start to react using your outputs. And your outputs are your hands and legs. You start to walk to different places, you start to reach out to grab different things, and that is how it works. If you don't have your senses, so your brain will not be able to process or to know what is what's happening around you. And if you don't have your outputs, you will process what is going around you, but you will not be able to do anything, really. You'll not be able to move, you'll not be able to pick anything, so it is not going to be useful. That's the same thing with the PLCs. From the input side of things, you can have all types of sensors. So it can be a proximity sensor that detects the presence of objects. It can be buttons, or it can be different temperature sensors, pressure sensors, elevation, any sort of industrially related sensors to the application that it is designated for. It can be all sorts of switches and buttons, physical devices that once they are pressed, they give a signal that, well, you should do this X, Y, or Z, or something happened, this button has been pressed, the start button has been pressed, for example, so start the machine, etc., start the sequence. And from the output side of things, you can have everything that applies force to the surrounding environment. You can have a motor, you can have lights, you can have a fan, you can have contactors, you can have pneumatic hydraulic cylinders, you can have all sorts of outputs or actuators that can apply force to the surrounding environment. So by now, I think we have, let's say, a basic idea of what is a PLC, what is automation. So the idea of automation, now we want to connect different inputs to a device, and based on a program that we write, we will create a sequence of operation, and based on our inputs criteria, we are going to, and the program that we wrote, we are going to apply certain forces or do certain actions by using the outputs that we have. So moving to our case study, it is all about hydraulic presses. Hydraulic presses in general, these are devices that exist in industry, and they are heavily used in industry to make all sorts of shapes and parts that are related to anything that we are dealing with. If we thought about the automotive industry, for example, so the body shop, all the different panels of a car, this is stamped. This has been stamped out of aluminum, for example, to different shapes, and this is happening using hydraulic presses. The same thing you can apply or you can see around at any product that is made kind of from any metal in general. So that metal is having a shape, and that shape has been applied or created by shaping that piece of metal using a hydraulic press. And when we think about it, we start to think about, well, hydraulic presses have different sizes and different operations capabilities, like how we can see here. This is a large, let's call it a large hydraulic press, down to manually simple hydraulic press that you can operate by your hands. The whole idea of using hydraulic is using oil, and using oil is the reason behind using oil is because of the high force that it can apply. So as we said, it comes in different shapes and different sizes, but typically this is the two basic ones that you can see. Some of them comes with a single ram, some of them comes with a double ram, triple, etc. So we are not going to get into the details of different hydraulic presses. Rather than all of what we need to know is that we have a system that operates using oil and oil pressure in order to apply force to different metals. So when we look at the evolution of hydraulic presses, we are looking into 4 generations of hydraulic presses. First generation, this is the manually operated hydraulic press, the very simplistic form of hydraulic press, something like this. It's a super manual. You are the one that is controlling this lever in order to allow for the pressure to be applied, for this ram to go down and apply force to a workpiece that is going to be placed in this area. So first generation, manually operated, just a basic mechanical valve to control it, basic pressure relief, operator dependent. Basically, the person that is controlling it is the person that is driving it. And then what we have the second generation. The second generation of hydraulic presses, these are electro-hydraulic systems that introducing relay logic. So remember when I said before the introduction of computers, and the whole idea was built using relay circuits and relay room for the control of production lines. This is the second generation as well of hydraulic presses. They don't have any intelligence, rather than it is the control of the motors, pumps, the reservoir, the return, the lubricants, the fan. All of this is happening using basic relay circuits. Efficient, it still works, it's still operating until now. I've seen hydraulic presses from the 60s and 70s and the 80s that are still operating until now. It is a system that is using the KISS principle, which is keep it simple and stupid, and it's still operating. But with this, we start to have certain limitations. And the certain limitation happens in the way that, well, I don't know how many did I make. I'm not able to monitor the state of the different devices within my hydraulic press. Maybe the oil pressure or temperature is very high. Maybe the fan or the cooling fan is not working how it should. Maybe the valves are not operating properly and they are having some sort of a leak. All of these different things are not able to be monitored or controlled. If you want to change parameters of your operations, it is down to very simple changes that you can apply for that hydraulic press, and a little bit of a lengthy process if you wanted to apply these changes. So things are not flexible as you would think. So you are kind of stuck to a certain product, to a certain parameters, based on what has been based on the setup for that hydraulic press that has been applied. With this, we started to see the third generation of hydraulic presses. So a third generation of hydraulic presses, these are presses that are using PLCs. So we started to have the smart element in this. We start to have a little bit of intelligence in our hydraulic presses. So now we can change parameters, we can monitor different areas, we can make sure that the system is working how it should, And the control system in general, the control panel of that hydraulic press is much more simpler. It doesn't have all the relays and all the connectivities, rather than we replaced a lot of them with the PLC that is holding the program of instruction to control that press. So with this, we started to have little bits of difficulties. So little bits of difficulties in the ability to interface with this hydraulic press, the ability to connect that hydraulic press to different systems. And that was one of the main issues and drawbacks of PLCs. PLCs, when they were developed and built, they were standalone systems. Remember the very first computer that you might have came across? I don't know your ages, but if you are old like me, you might have came across the time when internet was kind of not an easy thing, and you have to put in the phone line into the computer to connect. So in general, everything was standalone. The ability to connect to different systems and servers, that was not something that was common, really. So the same thing with PLCs. PLCs were standalone systems that are doing their jobs, and that was it. If you wanted to do any changes to the program, if you wanted to change the sequence of operation, it's not going to be as easy. And you're not able to connect that machine or that press or that system to any other systems or devices that can give you the ability to control it, to monitor it, to integrate it with a wider perspective of a SCADA system, as an example. And with this, we started to have the fourth generation. And this is with the fourth industrial revolution. So the whole idea now, we started to have interfaces. So we started to have screens with that hydraulic press or a system. And that screen will give us all the information that we want to know about the system, whatever it is. For the hydraulic presses, you can start to see what are the different temperatures, what are the different states of the valves, the motors, the pumps, all of these different elements with the safety system, the guard system of the hydraulic press. So we started to have that more of an interactive element within our systems. We started to have the ability to change different parameters based on our needs. So you can start to change the cycle time, for example, the time you're pressing part. Is it just a sudden press and you return the ramp up, or is it press and hold, for example, for a few seconds? The amount of pressure that you are applying, all of these started to have that dynamic ability and started to have the ability to change parameters. In addition, we started to be able to connect to different systems, to different devices. You might have seen lots of different videos and applications are coming across recently that now you can have a robotic arm that is connected to that hydraulic press for the loading and the unloading of parts. So instead of a person standing to operate the hydraulic press and push the start button, there is a robotic arm that is doing that job now. So a robotic arm will open the door, would put in a part, close it, wait for the cycle to finish, get a signal from the hydraulic press, well, the cycle is finished. The robotic arm will open the door, retract the part, put it away, get another part, etc. So the repetitive tasks that we are experiencing. So we started to have that ability, and we started to have the ability to connect to a wider range of systems. So that hydraulic press can be monitored and controlled using a SCADA system. And that communication ability can give really good insights into its operating conditions, the state of it, how it is performing, how many has been made, etc. And that is the latest and the fourth generation of the hydraulic presses. So looking into our case study, and before we get into this, you start to think about, well, whenever you see an old machinery, it is getting treated like an old car. If you have an old car that doesn't have all the bells and whistles and all what you might want, it doesn't have a screen, it doesn't have sensors for parking, or it doesn't have cameras, or it doesn't have whatever you might want, you might start to think about, well, I want a newer car. So I will sell this one, buy a new one that has all of this. The same thing applies as well with the manufacturing industry. But with the manufacturing industry, we have another option as well. Well, we can modernize what we have. If our machine is working properly, it doesn't have any issues, it has been maintained and looked after over the years in a good way, and we are taking very good care of that machinery, what is the reason behind changing it? Well, we need nicer, more fancier, more capable machinery. And at that time, I start to think about one of two options. Well, should I sell this machine and buy a new one? Or maybe it's better to use that machine and modernize it and make it capable like any modern machinery. And that was the case study of today. What we have a machine for a hydraulic press from the second generation. This hydraulic press is from the 70s. So what it is controlled with, it is controlled based on a relay logic. It doesn't have PLCs, it doesn't have anything. It is of a very good build, German build. It's a brand called Hiller. And that brand has been around for a very, very long time, still exists until now. Their presses are state of the art, really good. Well, we all know about the German build. And it has been maintained and looked after over the years in a good way. But again, it doesn't have any intelligence into it. It just have a relay control panel that is controlling the whole thing. And it needs a person that is standing here, something like this, to press these two buttons to operate the machine. Open that door, load in the parts, close the door, press the two buttons, two hands for safety, to not stick your hand somewhere that you shouldn't, and run the cycle, open the door again, and that's it. Not as easy to change parameters of that hydraulic press. The whole control system that you are having is this basic board that has different lights that can give you indications of the different state of the motors, pumps, doors, safety door, etc. But simplistic, doesn't have much going on. And our mission was to how can we get this hydraulic press up to the fourth generation. So we started following different stages of operation. So first thing, it was the investigation phase. So we studied the machine across all four domains, mechanically, electrically, hydraulic-wise, hydraulic system-wise, and then control-wise. We identified and found out what is this machine is about, how does it operate, what are the different integrities of all of these different systems. Mechanically, it was about the chassis inspection for any cracks, for the ram condition in motion. It can go up and down freely without any obstructions, without any issues. All the components are working how they should. Electrically, we looked at the motors, pumps, fans, sensors, and switches that the press had. Hydraulic-wise, we looked into the hydraulic fluid condition or the oil condition, the directional control valves, operations and conditions, all the different lines and connections, and the operation sequences. From the control-wise, we looked into what does it require in order to transform this machine from the very basic relay logic into PLC. In order to know this or to identify this, we have to very much understand everything within the machine. What are the different inputs to the system? What are the outputs that we require from the system? And with this, we start to identify the power requirements for each part as well. You have 380 voltage AC motor. You have 220 basic lubricant pump. You have a fan. You have different 24-volt DC limit switches to tell you where the RAM is. You have the guarding door for the system, which was manual, and we wanted to automate that as well. So we started to identify what are all the inputs to the system and what are all the outputs of that system. So the IOs for the system and all the power requirements for each of these parts. And then it was overall parts quality assessed confirm the machine is within safe operation conditions. And this is one of the things that is called pure requirements. So the pure requirements, it is a standard, like how in life we have standard for everything. And the pure requirement, it was there to identify and to make sure that everything is operational, everything is safe to operate, and everything up to the standards. That was the end of the first stage, and then we moved to the second stage, and this was the guard system design. What we wanted to do is we wanted to replace that basic door that is manually operated, so someone has to open the door, put the part, close the door, do the same thing for the retrieval of the parts, into something that is automated. So we designed a pneumatically operated door, so automatically operated pneumatic door, and it is basically a door that with the cycle end, it will open or will go up pneumatically using 2 pneumatic cylinders. Efficient, easy, saves time in order to make things much more efficient. So it was all about safety first approach for the integration of automation planning from the outset. So we wanted to know how could this be integrated? What are the requirements for it? Then we looked into the pneumatically operated PLC controlled guard door that is integrated, that would be integrated with the machine's PLC or main controller to physically isolate the press during operation. And this is, again, this is a requirement or standards requirement for any machinery to be operated within the UK. Everything must have its safety requirements and safety elements. We looked into how can we eliminate inhuman intervention that can have a risk during an active press cycle. So we have to make sure that the guard door is lowered, closed when the machine is operating, and the machine will not operate with that door open. We identified pneumatic position detector that is mounted inside the cylinders to tell us where that door is. So if it is open, a cylinder or a pneumatic cylinder, which typically something like this. So it's just a cylinder that extends and retracts. Typically we'll have a sensor here and a sensor here. And these two sensors will detect if it is extended or retracted. Because the extension and retraction towards the end of that cylinder, what you have a metal plate, and that metal plate can be detected by a basic proxy sensor. Then we started to move into stage 3, and these are the requirements on the identification stage. So all the electrical components selected to deliver the appropriate power ratings for each press component. Like how we said, you have all the different types of voltage requirements, whether it is a 3-phase, single phase, AC or DC, 0 to 10 voltage, 0 to 24 voltage, 4 to 21 milliamps, or 4 to 20 milliamps. All of these are different power requirements to different components in the machinery. So each of these needs that translator, let's call it in a very basic terminology. How can we translate a signal from the PLC that is typically operated using 24 volt DC in order to operate that AC elements or AC components, whether it is single phase 220 or 380 devices, or DC components that are 0 to 10, 0 to 24, or 4 to 20 milliamps. So all of these devices are operated using 24 voltage DC signal that is coming from the PLC. So lots of different mapping for all the different requirements must be done. And then it was about the PLC and the HMI, which is the human machine interface, the screen that is installed or that gets installed on the machinery in order to give you all the information about the PLC, all the information about the press, the state, be able to change parameters, count how many parts have been made, etc. And came to the connectivity elements, which was the identification of the PLC that is capable of talking OPC-UA. OPC-UA is the language. It's a communication protocol. So the whole idea, or what exists in the industry, that different PLCs had their own way of talking to each other. Each brand developed its own way. We started to have Siemens making their Profinet and Profibus. We started to have Allen Bradley and Schneider making Modbus. We started to have different ones in general that are specifically made for specific brands. But Industry 4 came with the OPC, or the unification of protocols. So it came around and said, well, all these brands of PLCs, all of you, next to your own protocols, make your devices able to speak in OPC UA. With this, we started to be able to connect a Siemens PLC to Allen Bradley PLC, to Beckhoff, to Schneider, to whatever, Cruzet, to anything, to Delta PLC. All of these PLCs are now able to connect and talk to each other. And then with this, after all of these assessments and identifications, we moved into the monitoring tools, because we wanted to have a really good idea of how things are happening and working. So we looked into the existing pressures and temperature sensors that are retained by but we enhanced them with additional sensing devices. So wherever we thought that we would need extra abilities or extra insights into the machineries, we added that. We added extra temperature and detection sensors to the main motors and the surrounding area in order to have that condition monitoring abilities for maintenance activities. We looked into the pressure and temperature deviations that are used as early warning indicators. So we needed to know when the parameters are different from what it should be. We looked into the early detection approach aimed at preventing failure before they escalate. So once something that happens, what would be the impact, or what would be the way to know about it? So what are the warnings, where they are going to be sent? How would we inform the users and the operators and the maintenance staff of any of these issues developing? The guarding system that we developed and its integration with the HMI screen to monitor its security and its operation. So all of this was essential elements to be able to operate safely and to retain the integrity of the machine itself. Then it was the last stage, which is the programming stage. So everything needs to be now to be integrated together and programmed. So PLC and HMI programming using ladder logic, and ladder logic is the language that we use to program the PLCs. So microcontrollers in general, well, you definitely heard about the C, C++, C#, Python, Java, all of these different languages. But for PLCs, it has different lists of programming languages. And one of them is the ladder logic diagram. And then it was the program that governs the machine self-control and monitoring without requiring any human intervention. We needed to automate as much of the process as possible, and with the reduction of any human interaction. We looked into the operation sequence and how can we have that operation sequence defined, and everything is working together within the machine, from the actuators, the pumps, motors, lubrication pumps, fans, all of this. And then it was about the HMI screen build. So we included the visuals that are required and the different elements that are required for operations, monitoring, and maintenance schedules for the machines on the screen as well. So everything can be automated and digital. We added the ability to adjust different thresholds, different parameters, so we can have better and more dynamic system. This was the control panel that has been developed after all in order to control the machine. So we used Schneider PLC and we used VFD in order to control the main motor and all the different relays to control the different parts. And for sure, we used the safety relays and all the circuit breakers that are related to everything within the machinery. And for sure, we had the very main circuit breaker. All the different terminal blocks that can connect all the different parts and components to the distribution of the control panel. As well, we had the PLC, the HMI screen. So we replaced that basic simple control panel with that HMI screen. So what you can see here, you can start to see that, well, we have a visual of hydraulic press with all of the indicators for the state of the limit switches across the RAM, and have all the valves and their status at the bottom, and different pages that can show the different parameters. And you can see here now we are monitoring the pressure of the system, and we are able to change parameters and have better and more dynamic abilities to that system. So we transformed that hydraulic press from a very basic, simple, old machinery into a modern, fully automated, dynamic system that can be changed, can be adjusted, and can have better output out of it. So this takes us to PURE. And PURE stands for the Provision and Use of Work Equipment Regulation. And this came across in 1998. So what PURE states that all work equipment must be suitable for its intended use and operating condition. All the equipment must be maintained in a safe and efficient working state with up-to-date maintenance records. Inspections and examinations must be carried out at appropriate intervals by competent person. Apologies. Adequate controls must be provided, including start, stop, and emergency stop functions. These are basic, very main requirements. We added the ability for us to start the cycle from the screen. This is easy and possible, but PURE states that you must have as well physical buttons. This is basically a redundancy elements in order to make sure that if anything wrong happened to the screen or whatsoever, you have that physical button that is more rigid in order to avoid any incidents. It states as well that equipment must be fitted with appropriate guarding to prevent access to dangerous parts. And this is what we did with the automated pneumatic guarding system. And then operators and maintenance staff must receive sufficient information, instruction, and training. So these are kind of key elements of the PURE requirements. But in general, what you see here, you see that this is a way that dictates how can a system be safe, how can a system be maintained and preserved for longer time, and what are the key elements that are required in order to make sure that this system can be operated, is safe, the people that are using it are trained, knowledgeable, they can do what they are supposed to do in an efficient and safe manner. So when we look at how this can impact or the developed system can have an impact on PURE, we start to see that the PLC controlled guarding system, again, this is tackling that first guarding requirements, automated emergency stop and interlock logic with the safety relay I mentioned, and the emergency stop button. All of these are there to tackle that safety element. OPC-UA, the communication ability. So this is enabling for data logging, to know what is happening and to have better records of the machines and its operations, its condition. Different sensors that are installed on the machine that can help to identify any anomalies and to help with better maintenance activities. HMI screen that gives the operator a real-time visibility of machine condition. Adjustable different alarms and thresholds that allow for the maintenance team to define and evidence any safe operating limits. And eventually the knowledge transfer program that was carried out to train the different staff, whether it was operators or whether it was the maintenance team, in order to be able to operate the machine and be able to maintain its efficiency and properly. And that was a successful project because it did show its impact straight away. We have a better system. We have a system that we know what is going on with it. We have a system that's dynamic. We can change things. We are always keeping an eye on different elements. We can know the status and the condition of different parts and components of that system. And all of that was very great additions that have been developed and added to that system. So when we look at what's next and how things can be developed, so what we find here now, or what the current state is that we are working in an environment, in an industry, that everything is happening in a sequence. From workstation 1, things would go to workstation 2, to 3, to 4. Again, think about the assembly process of any product that you might think of. If your mobile screen, if your screens, if your laptop, if it is a car, if it is a table, everything is following a specific set of process or sequences. And what we are trying to do, or what modern technology is trying to do, is trying to get that customization element into these production lines. I'll give you one basic example that can show you that it is happening. It is getting applied rapidly. Think about, and it's usually within the automotive industry, because automotive industry, they always have lots of money to spend. If you thought about cars in the past, like BMW, for example. So what you had in the past, what you only had, I don't know, 3 series, 5 series, if you know about cars, and 7 series. But yeah, 3, 5, and 7. Very basic 3 models, and that was it. And the reason behind it was the need to make and build a factory that costs billions for each model. So everything must be justified, really. It's not just about building a car, rather than building the factory that builds these cars. And that was difficult. It was not that easy to just spend billions to make to build different factories for every model that comes across, because, well, are we going to sell lots of these cars in order to make our money back or not? So everything, as I said initially, was solid, was static. The systems were not dynamic and not adaptable to different products. But what you can see now, you can see for BMW, you have the 1 series, 2 series, 2 series, 3 series, 5 series, 4 series, 6 series, 7 series, and 8 series, and a whole line of X's, SUVs, X1, X2, X3, 4, 5, 6, 7. So how did they make all of this? They didn't build a new factory for every variant of those. But this is the impact of technology. This is the impact of the adaptability that we have been talking and speaking about. Now they can produce different models out of the exact same production line. And that's because now they started to have smarter systems that are able to adapt and to change their parameters easily. You don't have to go into every PLC and change the parameters that it is programmed for, rather than from just the basic EMS system that you can change the parameters for BMW first series, second series, third, fourth, fifth, whatever it is, it doesn't matter. So you might see in a single production line 5, 6 different cars coming out of that production line. And that's because of that technology and development in these technologies. You can start to see how much capacity now has been increased, and the ability to produce more and to make much more different variants, especially the variants and that customization elements started to come across. So I hope that was useful. I hope that was informative, gave you good ideas of what is industrial automation, what is the current state of it, what is the future state, and which is actually happening now, and how can you benefit out of that. You should be learning to cope with this. This is a skill that is very much demanded. Not many people know about industrial automation as engineers or operators or whatsoever. So when you are in industrial automation that knows about this stuff, you are very much demanded. You are getting paid a lot of money because, well, you don't exist. It is one of the very short skilled engineers within the UK. There has just been recently an industrial report that highlights how much this is a very demanded skills for the manufacturing industry, to have the automation and robotics knowledge in order to equip the next generations with the ability to run these factories and to get up to speed with all of these technologies. So if you never thought about it, or you never knew about it, or considered it, or you're looking into the consideration of something that an area to develop your skills or knowledge or to educate yourself with, so I would always say that this is the go-to. This is very essential, very important, and very effective way to get yourself around. So that was it. Thank you so much for attending today. I hope this very little time was beneficial to you, gave you a little bit of information, ideas, eye-opening for how things can be done. So
Thank you so
looking
much.
into one of the questions, no, you're welcome, Como. So just jumping into a question very quickly from Emmanuel. How will automation integrate with current IT systems, data flow, and production processes? And this is what I just mentioned, Emmanuel, that there is something called EMS systems. So the EMS systems or the SCADA systems, these are bigger systems, and these systems are there to connect with all of these different controllers. If we talk about SCADA, and this is something that hasn't been new really, but it's been around for a while. A SCADA system is a system that can have the ability to connect to all the machineries in a single factory. It doesn't exist only in a manufacturing site, but it exists in transportation. For example, if you thought about how the metros and the trains are operating and how there is a room for monitoring and making sure all the trains are working how they should and they're not just hitting each other, it is a SCADA system, and each train is a controller or a PLC by itself, a system by itself, and everything has to work together. The modern way is the EMS systems. And these EMS systems, these are systems that are more agile and have more functionalities, and they can connect to different PLCs, different brands, different operations, and you can have that ability to adjust, monitor, and control them efficiently. So if you never heard of it, look into it, look it up. EMS systems, they exist now, and these are the driving force, like how I said, with all the modern factories, like how with the cars that can make all the different models from out of a single production line. And that's it. I hope that was useful. Well, back to you, Como.
Thank you so much, Dr. Shalon. And thank you to all our attendees for making it to today's webinar and giving us your attention. We truly do appreciate that. And just to wrap things up, we've got upcoming programs for higher education courses. We've got 2 bachelors and 2 masters, and the dates that have been put there, that's when the courses will be commencing. So we've got one intake for this year and one early on next year. So if you are interested, you can go ahead and just visit our website. I will give you the links for this shortly. And then for our short courses, these are our 3-month short programs, which are delivered through our affiliated institute, EIT. And we're currently running a promotion. They normally £933. But if you do apply before the end of November this year, it will be £599. So rounded off, that's £600. And all these, all the courses we have on our website, this discount applies to that. Okay. And then for the certificate of attendance, as I've mentioned, you've got 48 hours in order to complete the survey of the link I'm about to provide. But if you're not going to use the link, please capture the QR code that you see on your screen right now. And that will ensure that you receive the certificate of attendance, the slides, as well as the video recording of this webinar. So I will also include the links for our upcoming events. That's basically all the other webinars that will take place this year, and you can register for that if you are interested. So if you could just check the chat box, I have included all the links that are relevant to today's webinar, and as well as the link for the certificate of attendance. Once again, thank you all for attending and hope to see you in the next webinar. And Dr. Shalan, thank you for your insightful information as always, and see you next time.
Thank
Thank
you.
you all.
Thank you, guys. Bye.
Bye.